Okay, good morning all. So in the last class, we proved a very important theorem known as Rees representation theorem. So what we got, let me just recall. If H is a Hilbert space, then for any y in H, f sub y from H to C defined by f sub y. This can be C or R, so whatever the scalar is. F sub y of x is equal to the inner product of x with y. So this for any y, f sub y is a continuous linear functional, and also we saw that norm of f sub y is equal to norm of y. And this map, the map y going to f sub y from h to h star is conjugate linear. So that is f sub y1 plus y2 is equal to f sub y1 plus f sub y2, and f sub alpha times y is alpha bar times f sub y. So this is not a linear map, but this Rees representation theorem also says that this map is onto. So one thing note that this means that this map is an isometry. So this implies this map is an isometry. This is because for isometry, the distance between the image should be same as distance between the two points. So if we take y1 and y2, then f sub y1 minus f sub y2, this norm in H star, this is because f satisfies this property. This f sub y1 minus f sub y2 is same as f sub y1 minus y2, and we know that this is same as norm of y1 minus y2. So if y1 and y2 are 2 points, then their images are at the same distance as the distance between y1 and y2. This is in H. Also, important thing is that by Rees representation theorem, this map is also onto. So by the Rees representation theorem, the map y going to f sub y is also onto. So now we get an onto isometry. It is not linear, but it is additive and conjugate linear, and this is from H onto H star. So we go from H to H star, and also we saw that H star can again be made a Hilbert space by defining this inner product. H star becomes and becomes a Hilbert space with the inner product. So if we have any two element in H star that is of the form Fy1 and Fy2, so the inner product of any two element of H star, this can be defined as the inner product of y2 and with y1. Here the order has to be changed because this f sub y is conjugate linear, not linear. So then you can check that this defines an inner product on H star, and also this induces the norm of H star. So that is because if you see norm of any f sub y, that we know is equal to, by Rees representation theorem, that is equal to norm of y. So that will be equal to square root of y inner product with y, and then by this definition that is equal to inner product of f sub y with f sub y. So therefore this inner product, this induces the same norm which is on the Banach space H star. It's a Previously, we know that dual of any Banach space is a Banach space, but now we are showing that dual of a Hilbert space is also a Hilbert space, and then we can also talk about the double dual. So that is again a Hilbert space. H star star is also a Hilbert space. So we saw that for a Banach space there is a natural embedding of uh, x into x double star. It's double dual. Right? So we have so we know that there is a natural embedding of h into h double star. So this is considered as both are considered as Banach spaces. So there is a natural embedding of h into h double star given by this map that we defined. JA was the map from h to h double star. How this is defined as, so if we have any element x in H, then Jx should be in H double star. So Jx of F is equal to f of x for x belonging to H and f belonging to H star. Right, so this defines a linear map from H to H double star, and also we know that this is also an isometry. So J is linear and norm of Jx is same as norm of x for all x in H. Now, so this is one map from H to H double star, which is we know that for any Banach space we can define this map to double dual. But here we have another map on Hilbert space, which is this map x going y going to f sub y. Right? So here H is a Hilbert space. So we have another map from H. This map is actually on to H double star. So this is by composing the map from H to H star and H star to H double star. So by composing the maps H onto H star and H star onto H double star. So this is the map that if we have any x in H, then we have x is going to f sub x. So this x is in H, then f sub x is in H star, and then f sub x can be mapped to f sub x, which is in H double star. So we get another map which is x going to fx going to f sub x. So this gives a map from H to H double star. Also, we know that both these maps are conjugate linear. So x going to f sub x, this is conjugate linear, this is conjugate linear. This map here is conjugate linear. And this map is again conjugate linear. So the composition, this map, therefore the map x going to f sub x, this is linear and isometry. Right, because if we have any scalar multiple alpha x, then it will go to alpha bar of f sub x, and alpha bar f sub x, again this is conjugate linear, so that will go to alpha bar, so that is alpha times f sub x. So this also becomes linear So now what we see that there are two different maps. One was this map J, which is from H onto H double star, and another is this map X going to F sub X, which is also mapping H onto H double star. Both are linear, both are isometry. So in fact, what we see that these two maps are the same. So the claim is the above two maps from H onto H double star. So okay, so this uh, the first map J, we did not know whether it is onto or not. Right? We defined a reflexive Banach space if this map is onto, but here we only know that this is from H to H double star. But the second map we know is onto also. So right now we know that both are maps from H to H double star are the same. This is very easy to check. So let's check that these two maps are the same. So the first one is X going to F sub X, and the second one is X going to J of X, right? So let's call this other map as J dash. So let J dash from H to H double star be the map. So we have to define what is J dash of X. So J dash of X should be in H double star. So that means that we have to define what happens to the value of this at any point in H star. We want J dash X is in H double star. So J dash X of any F, how do we define? So note that any F in H star is of the form F sub Y. So we have to define what is J dash of X of F sub Y. So this is, we can define as, I mean, this is this map that X going to F sub X. So this is F sub X on F sub Y. Maybe let me just write this. J dash X is this map F sub X. This belongs to H double star for X in H. So we know how this F sub X is defined. So J dash X of any F. So again, let me write any F belonging to H star is of the form F sub Y for some Y belonging to H. This is again by the Rees representation theorem. So J dash X of any F, this is equal to F sub Fx acting on F is of the form F sub Y. And how this map is defined? So F sub Y of X was defined as inner product of X with Y. So this will be inner product of F sub Y with F sub X. Note that this inner product is in H star, right? Because these are element of H star. So this is the inner product. And how the inner product is defined on H star? This is equal to the inner product of X with Y, right? And so we claim that this J dash X is same as J of X for every X, right? So what is Jx of F? So this we know was defined to be equal to F of X. J was defined as Jx of F is equal to F of X. So let's see what is this. What is F? F is same as F sub Y. So this is F sub Y of X. And by the definition of F sub Y again, F sub Y of X is equal to inner product of X with Y. So what this shows that, so therefore J dash X of F is equal to Jx of F for every F in H star. This implies J dash X is equal to Jx. And this is true for every X in H. So therefore these maps are same. J dash is same as J. Right, so these two maps from H to H double star, these are same. So what we get is that, so hence we have the following theorem. Every Hilbert space is a reflexive Banach space. Of course, you can have reflexive Banach space which are not Hilbert space, but this says that if you have any Hilbert space, then it has to be reflexive. So the proof is clear now, right? Because we showed that this map J dash we know is onto, and by the above claim J is onto. Proof is since we know that the map J dash from H to H double star is onto by the above claim. J from H to H double star is onto. And this implies that H is reflexive. Okay, so now let me talk about okay, let me also talk about adjoint of a bounded linear operator on a Hilbert space, because again we need this representation theorem for that. So adjoint of bounded linear operators on a Hilbert space. So let T belong to B of H, that is T from H to H is bounded and linear. Then we want to define T star. So first let us prove. So, or maybe let me define. So a map T star from H to H is said to be adjoint of T if X inner product with T star Y is equal to Tx inner product Y for every xy belonging to H. So if there is some maybe let me say a linear map. So this in fact you can define on inner product space that if you have any linear map on an inner product space, then we say that T star is the adjoint of T if X inner product with T star Y is equal to the inner product of Tx with Y. So if there is such a map, so in general for an inner product space, so there need not be any such map. So a linear map need not have an adjoint, but for inner product space, if you have a finite dimensional subspace, yeah, if you have a finite dimensional inner product space, then on that any linear map has an adjoint. And more generally, here we are saying that if we have any Hilbert space, and if T is a bounded linear map, so in that case it has an adjoint, and this adjoint will also be a bounded linear map. So T star also belong to B of H, and then we'll see that it satisfies certain properties. So first of all, we have to show that for any T belonging to BH, there exists an adjoint T star belonging to BH. So existence of T star. So what we see that we have to define this map T star of Y, which will satisfy this equality. So how to define this T star Y? So T star Y we want to define. So here what we have is that we have this Tx inner product with Y, right? So if we have any Y, so let Y belongs to H, we want to define T star Y. T star of Y. So what we have, once you have Y, then let us look at this map X going to this inner product of Tx with Y. So consider the map F from H to the scalar field given by f of x is equal to the inner product of Tx with Y. So Y is fixed now, and we are defining this map X going to f of x. So and T was the given bounded linear operator, then we define this map F. Now what do we know about this F? So clearly this F is linear. That is because T is linear and the inner product is linear in the first component. So F is linear. Also, what is mod of Fx? This is equal to mod of Tx inner product with Y, and this is less than equal to norm of Tx times norm of Y. This is by Cauchy-Schwarz. And T is given to be linear, so this is less than equal to norm T times norm Y times norm X. So mod Fx is less than equal to this constant, which is norm T times norm Y times norm X. So this implies F is bounded, so F is in H star, and norm of F is less than equal to norm T times norm Y. So this map F is in H star. Now what do we know about F star? We know that H star, any map in H star is of the form F sub Y for some Y. So here we have Y, so we will write, so by the Riesz representation theorem, there exists a unique vector in H such that this f is equal to f sub that, right? So let's call that unique z sub y belonging to H such that f is equal to f of z sub y, right? So that is f of x will be equal to the inner product of x with z sub y for every x in H, right? So this representation theorem says that any AF in H star is given by f of x is equal to x inner product with a fixed vector, a unique vector in H. So because this f was defined using this y, so this actually depends on y also, right? So we are writing this vector, this depending on y. So for a fixed y, this is a fixed vector. So we have z sub y. So now we define this t star from H to H by t star of y is equal to z sub y. Because for every y there is a unique z sub y. So now we get a map from H to H. We get a map. Now what is the property of this map? Then we want to see whether it satisfies the property of definition of adjoint. So what is x inner product with t star y? Then x inner product with t star y, this is equal to x inner product with, this was z sub y, and this is defined as f of x. And what is f of x? F of x is tx inner product with y. So this satisfies x inner product with t star y is equal to tx inner product with y. This is true for every x in H and y in H. So it satisfies this. Let us check that this t star is also linear. Claim is t star belongs to B of H. So first the linearity. So if we take y1 plus y2, so x inner product with t star of y1 plus y2, this is equal to tx inner product with y1 plus y2, and this can be written as tx inner product with y1 plus tx inner product with y2, and again using the definition of this adjoint, this is equal to x inner product with t star y1 plus x inner product with t star y2, which is equal to x inner product with t star y1 plus t star y2. So note that we don't know t star is linear, so we cannot directly write this t star of y1 plus y2 is t star y1 plus t star y2. But here, by using the linearity of this inner product, then we can write like this. So what we get is that this is true for every x in H. So this implies this is true for every x in H. So this implies t star of y1 plus y2 is equal to t star y1 plus t star y2. right? Because for inner product, if I have x inner product y is equal to x inner product z for every x in H, then that says that x inner product of y minus z is equal to 0. That is true for every x. Then you can take x equal to y minus z to show that y minus z is 0. So this is simple. Similarly, if I have t star of any scalar multiple of y, x inner product with t star of any alpha y, this is equal to tx inner product with alpha y, which is equal to now we can take this alpha out. So this will be alpha bar tx inner product with y, and then we'll write this as alpha bar x inner product with t star of y, and then again we put this alpha inside the second component. So this will be alpha times t star of y. So this will imply t star of alpha y is equal to alpha times t star y. So therefore this t star is linear. We will also show that t star is bounded. In fact, we will show that norm of t star is same as norm of t. So how do we get that? Okay, so let's see. So t star so let's see. So so first let me show this. So note that for any x in H, norm of x can be written as supremum of mod x inner product with y, where supremum is over all y such that norm y is less than equal to 1. So why is this true? Let's prove this. So first of all, if we have if norm y is less than equal to 1, then mod of inner product of xy is less than equal to norm x times norm y. This is by Cauchy-Schwarz, and norm y is less than equal to 1, so this is less than equal to norm x. So therefore this supremum of norm y less than equal to 1, this is less than equal to norm x. Also if we have x is equal to 0, then of course this is true. So we can assume that x is non-zero. So if x is not equal to 0, then x by norm x let me write this. So supremum of mod x y norm y less than equal to 1. This is greater than equal to, I can take any vector whose norm is less than equal to 1. So I'll check x with x by norm x. And what is this equal to? This is equal to norm x only, because x with inner product with norm x, that is norm x square divided by norm x, so that is norm x. So supremum is also bigger than equal to norm x. So therefore we have that norm x equal to supremum of xy. So for x equal to 0, it is obvious. So we are assuming x is non-zero. And for x non-zero, we do like this. Because for x equal to 0, both sides are equal to 0. So we get this. So now let's look at what is norm of T star. T star okay, one thing we already know that this T star y, that norm is norm of z sub y, and right. So let's say, so therefore norm of T star of y, this will be equal to supremum of so by this we know that norm of x is equal to supremum of inner product of mod of inner product x with y. So we have T star y with x with norm x less than equal to 1, right? So this is norm of T star of y is supremum of mod of this inner product, and this we can write as supremum of, so this is also x with T star y, right? So this mod is same as x with T star of y, norm x less than equal to 1. And then by the definition of this T star, we know that this is equal to Tx inner product with y, and this is less than equal to norm Tx times norm y and supremum of norm x less than equal to 1. But supremum norm x less than equal to 1 norm Tx, that is same as norm of t. So this is equal to norm t times norm y. So this implies t star is bounded and norm of t star is in fact less than equal to norm t. Right, so t star is in BH and norm t star is less than equal to norm t. Let's see what is a t star star. So we said that so for any, so what we get is that for any bounded linear operator T on a Hilbert space, T star is also a bounded linear operator and norm of T star is less than equal to norm of T we are getting. We will actually show that norm of T star is equal to norm of T. So for that, let's look at what is the adjoint of T star. Since T star is in B of H, we can talk about adjoint of T star also. So since T star belongs to B of H, T star star, this is just the adjoint of T star. This is also in BH and we'll get that the norm of T star star will be less than equal to norm of T star by the above. But what is T star star? T star star is same as T. This is again just checking this. So if we have any we have to show that T star star of X. So if we rewrite T star star X with Y, this is same as X with T star of Y. This is by the definition of adjoint of T star, right? So if we write here, sorry, so T star star. Let me write like this. So how we define this T star, that if I have X inner product with T star, then that is same as T. So if we have T here, then it goes T star in the second component. So let's write like that. So I'll write Tx inner product with Y, that is X inner product with T star Y, and then this is same as T star Y with X complex conjugate, so bar, and now we have T star here in the first component. So this is equal to the complex conjugate of Y inner product with T star star of X bar, right? Because if we had T here, then it goes T star Y here. So we have T star here, then it will become T star star. And then again, we can write this as T star star of X with Y. And this is true for every Y in H. First we fix any x in H, and then we look at this. This is true for every y. So this will imply that Tx equal to T star star x. And this is true for every x in H. So therefore T, the adjoint of adjoint is same as T. So this is one property, and therefore we have norm of T star is equal to norm of T. So this is one important property of adjoint, that norm of the adjoint of an operator is same as norm of T. So this is because we already had norm of T star is less than equal to norm T, and then norm of T, which is norm of T star star, which is less than equal to norm T star. So this we get norm T is also less than equal to norm T star. So T star is linear, it is continuous. Norm of T star is same as norm of T. Also, you can see that, let me write that this as an exercise. So this T going to T star. So if I have T1 plus T2 star, this is equal to T1 star plus T2 star. This is very easy to check. And second is what happens if I take scalar multiple. So alpha times T star. If alpha is any scalar, then this will be equal to alpha bar times T star. Here alpha belongs to F. Right. So this T going to T star is again a conjugate linear map. It is not linear. You get conjugate linear. And also this is easy to check. If we have T1 and T2, we know that we can even take composition. So we can take T1, T2. So if I take the adjoint of T1, T2, that is equal to T2 star, T1 star. All these properties actually you would have seen for adjoint of a matrix. So for a square matrix, we define adjoint as by taking the transpose and complex conjugate of each entry, and then it is easy to check all these properties satisfied. And here we are saying that this is satisfied for this adjoint operator also. And one more important thing that maybe I'll prove next time also. So the norm of T star T, this is equal to norm T square. So this is again a very important equality. So you can try, otherwise I'll prove this next time and then explain why that is important. So after this, I'll define like self-adjoint operator, normal operator, unitary operator, and then some properties of that. And then we'll talk about orthonormal basis for a Hilbert space and some properties of that. And we'll come back to this adjoint thing later also. So let me stop here.